pour démarrer, on reste 2 secondes et après on enlève tout pour quand Natacha.
Ouais.
D'accord?
D'accord.
Donc, bon, ben, Natalia, Kharchenko, Natacha, nous vous invitons à vous présenter vos travaux pour 45 minutes sur Lattice algorithme and Lattice-based cryptographie. Donc, on vous écoute et après on passera aux questions. Voilà. À tout à l'heure alors.
Okay, thank you. Thank you everybody for coming to this Zoom conference event. Today I'm going to present my thesis entitled Lattice Algorithms and Lattice-based Cryptography, supervised by Antoine Joux. So is it okay? I mean, for everybody with the sound? Aren't there any trouble? Cool. Okay.
Okay.
Probably it's okay. So let's start. My thesis is about lattice-based cryptography. And so first, let's say a few words about why lattices are interesting for cryptography. So the first reason is the quantum computer. Now the vast majority of existing crypto constructions are based on RSA or discrete logarithm-based constructions, and they are completely broken by Shor's algorithm on a quantum computer. And for lattices, the situation is different, and they seem like a promising alternative in the quantum computer world for several reasons. And one of them is that lattice-based cryptography is already existent for more than 20 years, and there are many lattice-based constructions for many occasions, starting from basic encryption schemes or signature schemes to more difficult constructions like identity-based encryption or fully homomorphic encryption, when we can do some operations over encrypted data without decrypting it. And another reason is that lattice problems are very appealing to cryptography, because for some lattice problems we have the reduction from the worst case to average case. So some lattice problems are as hard on average and as in the worst case, and for cryptography it is a very nice feature. So before we go to the results of this thesis, we first recall some background information about lattices. And we start with the definition, and we can see lattice as a regular grid in the n-dimensional space. For example, here on the picture we can see a two-dimensional lattice. And a lattice can be represented by its basis, which is a set of linearly independent vectors. And a lattice is formed by all integer linear combinations of its basis vectors. And actually, a lattice can have infinitely many bases, switching from one to another by unimodular transformations. For example, here we have on this picture this nice basis formed by these two vectors, but actually there can be another pair that will span all the lattices, and not so nice one. But lattices have a nice invariant. Each lattice has an invariant connected to it called the volume of the lattice. And the volume of the lattice is the same for all the bases of the lattice, and it is equal. It can be defined as an absolute value of the determinant of its basis, or geometrically it is the volume of the fundamental parallelepiped spanned by its basis vectors. You can see it here. Another invariant connected to the lattice is its shortest vector. So lattice is a discrete structure, and naturally it has the shortest non-zero vector. For example, here it is this one. And the length of its vector is also important lattice value. And we have a connection between the length of the shortest non-zero vector and the largest volume given by the Minkowski theorem. So essentially it says that the length of the shortest non-zero vector is always small or equal to the square root of the dimension of the lattice times the volume of the lattice to the power 1 divided by the dimension. And we also sometimes for random lattices we can say that Minkowski's bounds become, how to say, tight because we have the Gaussian heuristic. And the Gaussian heuristic states that if we take a nice set in the n-dimensional space and count the number of points inside this set, then this number will be close to the volume of the set divided by the volume of the lattice. And from the Gaussian heuristic, we can deduce an estimate for the length of the shortest non-zero vector, which will be essentially close to the Minkowski bound. And in the rest of the studies, most of the time when we are saying that we have an algorithm that finds the shortest vector of the lattice, we usually mean that we have an algorithm that finds a vector of the lattice of this length, of the length given by the Gaussian heuristic. So now we can turn to the two most important computational hierarchy lattice problems, the shortest vector problem and the closest vector problem. So in the shortest vector problem, we are given a basis of a lattice, be some random one, not necessarily nice and short. And our goal is to find essentially the shortest lattice vector, or in other words, the vector of length equal to its first minimum to lambda 1. In the closest vector problem, we are given again some lattice basis and a target point in space, actually any target point. And our goal is to find a lattice vector V that is the closest one to the target T. So the best approximation of T with the lattice vector. And these two problems are known to be NP-hard. For SVT, it is NP-hard under randomized reduction. So we don't expect fast algorithms for these problems unless P is not equal to NP. And now I recall in short which techniques exist for solving these two problems. So there are actually many techniques. So here we concentrate on the record-beating ones. First, the fastest provable algorithm for solving these two problems is based on the discrete Gaussian sampling, and it is exponential both in time and in memory. But in practice, actually, usually either enumeration algorithms or Hume algorithms are used. Enumeration is better in terms of memory consumption. It requires only polynomial amount of memory. And the fastest in practice, or how to say, asymptotically fastest heuristic algorithm for solving SVT are Sieving algorithms. And the fastest Sieving algorithm now achieves the following constant in the exponent, which is, as you see, much better than the fastest provable algorithm. But it comes at the cost of having also exponential memory requirements. So in this stages, we are mostly concentrated on Sieving algorithms. So I will recall in short how the general idea of this algorithm. So how does it work? So essentially, it can be a Sieving algorithm can be divided in two steps. The first step is sampling step. So at the sampling step, somehow we generate a long list of lattice vectors with bounded terms. For example, if we have some lattice basis, which is not very good, but you know that it is somehow bounded, for example, it is given by LLA reduction, we can generate a lot of lattice vectors using this basis. So this is the sampling step. In the Sieving step, we look at all the differences from our list which we generated previously. And we look at their differences. As all these vectors are lattice vectors, their differences are lattice vectors again. And since we have a long list of lattice vectors, with some not very small probability, we will obtain some pairs that are shorter than the initially sampled vectors. So we keep these pairs for the next iteration. And thus, if we have a long enough list in the beginning, we can generate quite a lot of differences, which are shorter, so we are making some progress. And then we can repeat the seeding step, apply it again to the list we just obtained. And we repeat it until we have find a short enough lattice vector. And usually, in heuristic seeding algorithms, we need some assumption to analyze the complexity of the algorithm, because it's quite hard to capture the distribution of lattice vectors because it's a discrete structure, and also because it's quite hard to track all the differences. So usually, to analyze the complexity of the algorithm, people assume that the vectors from the list at each iteration behave as they are independent and uniformly distributed on a sphere of a corresponding radius. So further in the presentation, I will refer to such an algorithms as a spherical seeding algorithms. And now we are ready to go to the results of this thesis. So in this thesis, we proposed a new family of heuristic seeding algorithms called the cylindrical seeding. And essentially, the new idea here is that we have a different geometry of lattice vectors during the seeding process. But in the same time, it is in line with other seeding algorithms in the sense that we iteratively obtain shorter and shorter vectors. So how does it work? Before we go directly to the algorithm, first we recall the shape of a prime volume lattice. Assume that we have an integer lattice with a prime volume. So the lattice lambda with prime volume p. And if we look at the Hermite normal form of this lattice, we will get the following matrix. So it will be the matrix, which is essentially the right low corner is a huge identity matrix, and the first row is P, which is the volume of the lattice, and then some numbers that are smaller than P, some numbers modulo P. And then for lattice of this shape with such a basis, it is easy to generate a long list of lattice vectors such that the last n-5 coordinates here they denoted by x1, xn1, n-1, so that this last n-1 coordinates are short, while the first coordinate is huge, because we actually assume that the volume may be huge. It is probably 2 to the power some polynomial dimension. But it is huge, but it is bounded by p, because we have this first vector, which is p, and all the rest are zeros. So for this kind of lattice, we can create a seeding algorithm with cylindrical geometry. So how does it work? So first, we describe how it works for the prime volume lattice. Again, we have the initial generation step and the seeding step. In the initial generation step, we generate a lot of lattice vectors that lie inside a long and narrow hyperseeding. How do we do this? So first, we enumerate all the integer vectors in dimension n-1 that are short, which means that they lie inside a ball of radius of range square root of n, square root of small n. And then for each such vector, we can compute a lattice vector essentially in the way we've just seen. So we just compute the scalar product of our U with our A and take it modulo T. And thus we obtain a lot of lattice vectors that lie inside a hypercylinder of shape P and of radius close to the square root of n. And then we have a seeding step. In the seeding step, how do we proceed? First, we have a long list of lattice vectors such that their first coordinate is bounded and which is long, and the last and minus one coordinates also have bounded norm, but we assume that our first coordinate is much bigger than our last coordinate. So our goal essentially to achieve shorter vectors in the end. And in case of cylindrical geometry, this goal translates into achieving vectors which are much shorter in terms of the first coordinate. Okay, this V1 should be less than initial height divided by some decrease rate capital M. And the last and minus one coordinates should form vectors that are smaller than R times gamma, where gamma is some constant that is bigger than 1. So we let our last n minus 1 coordinate slightly grow. And so now it's quite hard to write a pseudocode for this algorithm, so I'll try to explain in the picture the intuition how it works. So here we have a hypercylinder of some height h, and we divide it into n pieces of the equal length. And then inside of each of the n pieces, we perform independently the usual spherical sieving algorithm with the parameter gamma. Actually, the parameter gamma is kind of complexity defining parameter for this algorithm. And how do we perform sieving? For example, we take this is hyper sub-cylinder, and we consider all the pairs of vectors. And now we just completely ignore the first coordinate because we know since they are all in the same hypercylinder, their difference will be good for the next step. So we just look at the last n minus 1 coordinate of the difference and check whether it satisfies the second condition. And if it satisfies, it goes to the next iteration. So that's how the algorithm works. And what is nice here is that the separating our vectors into the different chunks can be performed very efficiently, because what we need to do to ensure that we just need to sort all our vectors by the value of their first coordinate. Okay, so now we've seen the general idea of how cylindrical sieving can work. And now we can go to the complexity that we obtain with such an approach. So to analyze it, again, since it's quite hard to follow the distribution of the vectors during the iteration, we need some heuristic assumption. And actually, this heuristic assumption is quite close to what we have in usual sieving. So we just assume that the vectors formed by the last n minus 1 coordinate of the vector from the list behave as independent and uniformly distributed on an n minus 1 dimensional sphere. And here we don't need to assume anything in the first coordinate because we are just happy enough with the fact that it is bounded. And so what the complexities do we get? So when we fix our target length of the vector, which is the Minkowski bound, essentially the complexity defining parameter is gamma, the parameter of the growth of the last n minus 1 coordinate. And here we essentially have a family of algorithms parameterized by gamma. And here on this side, I have a complexity for two remarkable values. The first one is square root of 2. And for gamma equals square root of 2, we get 2 to the n divided by 2 time and memory complexity. Of course, it is worse than the complexity of the fastest heuristic sieving algorithm today. But what is interesting here and what we are going to use later is that for this parameter gamma, the complexity of the spherical sieving inside one chunk of the hypercylinder is small. Essentially, it is polynomial in n because, how to say, intuitively, it comes from the fact that if we take two random vectors on a sphere, with high probability, their angle between them will be close to 90 degrees. And this is essentially captured by the square root of 2, and this gives us this efficient spherical sieving path. And another remarkable value of gamma is 3 over square root of 2, and it's just taking gamma to optimize the time complexity. So, and if we optimize the time complexity of this algorithm, we actually achieve the same complexity as Baker-Joux over lattice-sealing algorithm, which was the fastest sealing algorithm, I think, in the 14th year. But now, okay, it's not outperformed, but still it's an interesting connection with existing algorithms. And so now what we've done is it was for the prime volume lattices. And actually, what we need to change the initial generation step, because we then can perform the sealing step in the same way as we just described. But the initial generation is different. So there is, and what helps us to generalize its algorithm is the unbalanced reduction. Using the unbalanced reduction algorithm by Gamma, Izobachenian, Nguyen, and Xi, we can obtain, for an given an arbitrary lattice basis, we can obtain a basis such that its first vector, the first vector of this basis is quite long. So it's essentially the volume of the lattice to the power 1 over n times some 2 to the n squared factor, which is huge. But if you look at the rest of the Gram-Schmidt vectors of this basis, they are actually going to be very short. So this is both in line with what we had for the prime volume lattices, actually. So we have, how to say, a projected sublattice, which has a very short basis, and we have also one direction which is long and which we shall reduce next. And besides having such a geometry, this unbalanced reduction also reveals an n-1 dimensional projected quasi-orthonormal sublattice where the enumeration can be performed very efficiently. And so how the initial generation in the arbitrary lattice case works. So first we just enumerate all the short vectors in the n-1 dimensional projected sublattice, and then we reduce obtained vectors with the first vector, and thus we again obtain a lot of vectors that lie inside the long and narrow hypercylinder. And then we can proceed as before. But the complexity of the algorithm is going to be different because for integer lattice, we have a more efficient algorithm for enumeration. So on this slide, essentially under the same heuristic assumption, we obtain the following complexity for the general case. Here we have the parameter gamma again, which defines the complexity, and 3 columns: the sieving time, which is the time essentially of the sieving procedure once we already have generated vector. Then we have initial generation time and memory consumption. And here we have 3 remarkable values of gamma, again square root of 2, because it's efficient for the spherical sieving step. The 3 over square root of 2 because it optimizes essentially the row sieving time. And also another value, which is close to 1.1, which optimizes the overall complexity of the algorithm, because now the initial generation time, as you see, it's slightly bigger than before. So in general case, we essentially have the same algorithm, but with slightly more heavy initial generation complexity. So to continue, we have found several applications where the cylindrical sieving can be very efficient and can outperform existing lattice sieving algorithm. And the first such special case is lattices with small prime volume. And to explain why it's efficient for lattices with a small prime volume, I will first give a simple example to give some intuition. So assume that we have, again, a lattice with a small prime volume, which is close to 2 to the n. And assume that we want that we, we tune our SIN algorithm in such a way that each time the first coordinate of the vector decreased by the factor 2 to the n over 4. And then, after 4 iterations of cylindrical series, we obtain completely reduced first coordinate. So it will be of some constant rate. And for the last n minus 1 coordinates, if we keep like the easiest mode where we have polynomial time complexity for the spherical string part, essentially when the factor gamma, the growth factor gamma is equal to square root of 2, we will obtain the following value. So our last coordinate will grow just by some constant factor, which is 4 here. So essentially the complexity of this algorithm will be ignoring the polynomial factors 2 to the n over 4, and we will obtain a constant factor approximation of the length of the shortest vector of the space. And so inspired by this example, we looked at the complexity of the cylindrical sieving for such lattices when their volume is close to 2 to the power n times some constant c. And here on this picture, we have a graph where the horizontal axis essentially represents the value of this constant c, and the vertical axis represents the constant in the exponent. And here the green line is the complexity of the fastest existing sieving algorithm, and the blue line is the complexity of our cylindrical sieve. And we see that for actually small values of the volume of the lattice, essentially when it is smaller than 1.7, we get a faster algorithm, which is nice. This is the first application. And the second application is connected to the closest vector problem. Essentially, we can show that the cylindrical things can be very useful for solving the closest vector problem with preprocessing. And before we go to the closest vector problem with preprocessing, we first let's see how, in general, cylindrical thing can be used for solving for approximating the target points with lattice points. So this is not an algorithm, this is just something like an intuition about how it works. So assume that somehow we have target points, which are denoted in this picture by red crosses, that are inside the initial hypercylinder of our cylindrical thing, and that we want to approximate them. And we also have these blue circles, which represent the lattice points in the same hypercylinder. And essentially, if we were able to move these red crosses, which represent the target points, to the next hypercylinder, we will obtain a better approximation for this target. Because, let me explain. So first we have these target points inside the hypercylinder, and also the lattice points inside the hypercylinder. And if you want to solve CVP, we can essentially first reduce the lattice points with each other, as we did before, and they will go to some squashed hypercylinder, which is shorter but a bit wider. And then we can reduce the target points with some lattice points in the same manner. So we want to find a pairs that consist of a lattice point and of a target point such that they are close to each other, so the difference fits in the next hypercylinder. And as every time, and then we can proceed iteratively like that. And in the end, we will obtain a very small hypercylinder where will be a lot of lattice points and target points inside. And once we will find such a small target, we will be able to recover an approximation with the lattice point to this target, just because each time when we proceeded, we subtracted a lattice point from this target. So if we subtract the final target from the initial target, we will obtain a lattice vector, which will form a nice approximation. So that's the general idea on how we can solve a batch of CVP problems using the cylindrical series. But here we have some small drawbacks. First, we have to have our target inside the hypercylinder, and essentially it's the main problem. So now we are ready to move to a little bit more precise description of solving the closed vector problem with preprocessing using cylindrical series. So in closed vector problem with preprocessing, we are essentially first given a basis of a lattice, and we can spend an infinitely many time on the preprocessing. And then when the target points appear, we should be able to just to find approximation for this target point more efficiently using the information obtained during the preprocessing stage. And here, so how preprocessing works in cylindrical series. The preprocessing is essentially equivalent to running the cylindrical series for solving SVP, as we described before. But now, each time, at each iteration, we store the state of the list of lattice points. So now, for example, we will store all the content of this hypercylinder and this hypercylinder and all the next hypercylinders. And this will be our preprocessing scheme for the decoding stage. Of course, it will have exponential phase. And in the decoding stage, we are given a target point, and we want to recover a closed vector space. And the decoding stage consists of two parts. So the first part consists in putting the target point inside of a hypercylinder. So we can have a target point essentially anywhere, but we want to connect it to some target inside the hypercylinder. And this can be done by reducing the target point with the right basis using the nearest planar frequency. And here we have the difference between the prime volume case and the general case. In the prime volume case, we reduce our target with essentially the basis given by the Hermite normal form of the legend, which we already discussed. And in the general case, we reduce our target with the basis given by unbounded reduction, also with the basis which possess like similar geometric properties. And then once we get the target inside the hypercylinder, we just iteratively reduce it with each list until we obtain a very small target, which will help us to recover the solution. So that's the general idea of the algorithm. So now we can move to its complexity. And to analyze solving the closed vector with preprocessing using cylindrical series, we actually need a different heuristic assumption. And essentially, we need some assumption on the behavior of the target vectors and on the behavior of the lattice vectors from the list that we produce during our preprocessing stage. For the target vector, we assume that it is uniformly distributed inside the corresponding hypercylinder at each iteration. So this is something that we need for the analysis, and it is kind of hard to prove, but it's something that we can obtain in practice if we re-randomize our input points, because we can re-randomize our target points by adding a random lattice vector to them. Another assumption that we use is the assumption on the lattice vectors from this. The first assumption, essentially, we assume that they are quasi-uniformly distributed. What does it mean? They are quasi-uniformly distributed inside the corresponding hypercylinder at each iteration. Essentially, it's some relaxation of the assumption that they are just uniformly distributed there. Essentially, we assume that for the last n-1 coordinates, we have the same assumption as before. So we assume that they are independent and uniformly distributed on a sphere. And for the first coordinate, we have some assumptions that is less strict than assuming that it is just union. So essentially, we assume that in any not too short interval, the probability to get inside this interval is proportional to its length, if we describe it informally here. And under this assumption, we get the following complexities given by this table. Essentially, here we are interested in the preprocessing time, the memory consumed by the preprocessing, and by the complexity of the decoding stage. Okay. And here we again have a difference for the prime volume case and for the general case, because we still have the same situation with the initial generation. So we are now it's time when we are really become interested in the fact that spherical sieving takes a polynomial time, because that's what allows us to achieve polynomial time decoding complexity. Because essentially, decoding is consists in finding a short, a closed vector to the target in the given list of lattice points. And since essentially we can do it in the logarithmic time of the size of the list, because we store our list sorted by the value of the first coordinate. So we, at the cost of spreading 2 to the n over 2 times on the preprocessing, we can obtain the polynomial time complexity of the decoding. And in the general case, we have slightly bigger number in the extent. So that's all for the cylindrical sieving part. And now we still have a little bit more time to talk about the second part, which is the hybrid dual attack on the LWE and the security estimate of the TFHE scheme. And this part is based on a joint work with Thomas Pitolo and Antoine Joux. So this part is inspired by the security estimation of the fast fully homomorphic encryption scheme over torus, which is currently one of the fastest fully homomorphic encryption schemes. I believe it's the homomorphic encryption scheme with the fastest gate bootstrapping at the moment, and its security is based on the LWE problem, the learning with error problem. More precisely, on a small secret version of the LWE problem. Essentially, in TFHE, we are in the scale invariant mode, so everything is defined over a torus on the interval, on the 0-1 interval. And we can define the LWE distribution as follows. So let S be the secret, which is binary, which is essentially small secret setting. And let C be some Gaussian-like distribution, which is centered and which has a relatively small variance. And the LWE distribution is essentially obtained by sampling A uniformly at random on the n-dimensional torus, and then sampling the arrow E from our distribution C, and then returning a pair that consists of A and the scalar product of A with the secret plus some small error. And the diffusion version of LWE problem consists in distinguishing between the LWE distribution and the uniform distribution, and the search LWE consists in recovering the secret. And this problem, the LWE problem, is known to be as hard as certain worst-case lattice problems, essentially as some approximate version of the SET. And in the original security estimate of the TFHE scheme, the authors used the dual distinguishing attack to estimate the security. Here we recall in short how it works. So the dual distinguishing attack is for the, more for the diffusion version, and it works as follows. So we are given several samples from the LWE distribution or from the uniform distribution, and we need to get the distribution. So if these samples are from the LWE distribution, then we know that for the matrix form, we have the following equality given there. And now assume that we are somehow able to find a linear combination of the vectors a1, am, such that it is short. So such that this vector, the vector x, is short. Then if we multiply the right part of our sample, the b, by this vector, we also should obtain something short, just because we know that this part will be short, and this part is short because the secret is also relatively small. And if it were samples from the uniform distribution, we should just get something uniform and not small. And that's essentially the idea of the dual attacks. Once we found such a vector, we just need to distinguish between some concentrated around zero distribution and the uniform distribution. And the vector v usually can be found using some lattice reduction algorithm. And we propose an improvement for this dual distinguishing attack, which essentially consists in hybridizing this attack with some sort of exhaustive search for the part of the secret key. Essentially, what we do, we divide a matrix, the matrix of LW samples, into two parts, and we correspondingly divide a secret into two parts, S1, S2, and A1, A2. And now we can rewrite this equality for the LW samples into the following equality. So now we have two parts, A1, S1, and A2, S2. And then we also apply lattice reduction to recover the vector v, but now we are doing it in a smaller dimension. So now we are doing it only for one part of the secret key. And thus, when we multiply our, rewritten equality by v, we will just obtain a new fresh LWE sample that will correspond to the secret key S2, and it will be obviously of smaller dimension, but the noise will slightly grow just because of this linear combination. And then we just can use exhaustive search to recover S2. And the exhaustive search step actually can be quite efficient in the case of small secrets, because now, for example, in the TFHE case, we have binary secrets, and we can just do this evaluation, which we need for the exhaustive search, very efficiently because of its recursive structure. And that's essentially the general idea of our attack. And now we are coming to the result, to the numbers that we have taken. And first, before we go to the numbers for the TFHE parameters, I want to recall that TFHE parameters, while we were doing this work, they were updated. And before, as I said, they were estimated using the dual attack, and now they are estimated using Martin Albrecht's LWE estimator, which found out that the most efficient attack for the parameters of TFHE is the primal unique SVP attack. So on this picture, actually we provide a comparison for the two attack, for our dual hybrid attack, and for the primal unique SVP attack for a wide range of parameters. And here, actually the horizontal axis represents the dimension of the problem, and the vertical axis represents the noise parameter of the LWE problem. And on the picture, the color represents the difference in the logarithmic scale between the complexities of two attacks for different parameters. And we can see that actually the two attacks are quite close. Here we use the Sieving model of lattice reduction, and under the Sieving model we find out that indeed the attacks give close results, but when the dimension is high and the noise is small, the unique SCP attack outperforms our attack. It corresponds to the red region on the heat map, and in other cases, our attack is slightly better. Okay, and finally, we have the numbers for the TFHE parameters. Here are the parameters of TFHE. I think it's the parameters from the last version of the paper. And we here compare our hybrid dual attack with the dual attack and with the primary unique SCP attack. And we can see that under all models of lattice reduction, essentially, when I say the model of lattice reduction, it means that which algorithm is used as SCP oracle. Here, Fully for enumeration, and here is also some extrapolation model, which is now, I think, is already a little bit outdated. And for each of the models we see that our hybrid dual attack performs better than both dual and primal. Essentially, in the most interesting Sieving model, we do not gain a lot. We gain something like 9 bits for the switching key in the compared to the most efficient primal attack, but we have some improvements. So I think that's all for the TFHE scheme, and this brings us to the conclusion of my presentation. So to sum up here in this thesis, we proposed a new species of heuristic Sieving algorithm and an improvement of the dual attack, which leads to the estimation of the security of the TFHE scheme. And so that's all for me, I think, and thank you very much for your attention.